Hello student, welcome back. We are going to start today's session. It is lecture 2, module 2, Microcontroller and Embedded System. Shongita Roy, Assistant Professor, Electronics and Communication Engineering Department, Narula Institute of Technology. Today's content is 8051 addressing modes and instruction set, different addressing modes of 8051, Boolean variable manipulation, program branching. Intel 8051 microcontroller instruction types. The 8051 microcontroller instructions are divided among 5 functional groups: arithmetic, logical, data transfer, Boolean variable, program branching. Arithmetic instructions. The arithmetic instructions are grouped together. Since 4 addressing modes are possible, the add A instruction can be written in different ways. Add A, 77ph, direct addressing. Add A @RO, indirect addressing. Add A R7, register addressing. Add A #35H, immediate addressing. All arithmetic instructions execute one machine cycle except the INC DPTR instruction, 2 machine cycles, and the MUL AB and DIV AB instructions, 4 machine cycles. Note that one machine cycle takes 1 microsecond if the 8051 is operating from a clock of 12 MHz. The 8051 provides powerful addressing of its internal memory space. Any location can be incremented or decremented using direct addressing without going through the accumulator. For example, if internal RAM location 7FH contains 40H, then the instruction INC 7FH increment this value, leaving 41H in location 7FH. On the INC instruction operates on the 16-bit data pointer. Since the data pointer generates 16-bit addresses for external memory, incrementing it in one operation is a useful feature. Unfortunately, a decrement data pointer instruction is not provided and requires a sequence of instructions such as the following: DEC DPL, decrement lower byte of DPTR. MOV R7, DPL, move to R7. CJNE R7, #0 FFH, skip, if underflow to FF. DEC DPH, decrement high by 2, skip. The high and low bytes of DPTR must be decremented separately. However, the high byte DPH is only decremented if the low byte DPL underflows from 00 to FFH. The MULAB instruction multiplies the accumulator by the data in the B register and puts the 16-bit product into the concatenated B high byte and accumulator low byte registers. DIV AB divides the accumulator by the data in the B register, leaving the 8-bit quotient in the accumulator and the 8-bit remainder in the B register. For example, if A contains 25, that is to 19H, and B contains 6, that is to 06H, the instruction DIV AB divides the content of A by the content of B. The accumulator is left with a value of 4 and B accumulator is left with a value of 1. 25 by 6 is equal to 4 with a remainder of 1. For BCD binary coded decimal arithmetic, add and add C must be followed by a DAA decimal adjust operation like a microprocessor operation to ensure the result is in the range of BCD. Note that DAA will not convert a binary number to BCD. It produces a meaningful result only as a second step in the addition of the two BCD bytes. For example, if A contains the number BCD 59, that is to 59H, then the instruction sequence is add A hash 1 DAA. Logical instruction. The 8051 logical instruction perform Boolean operation and or exclusive or and not on bytes of data on a bit by bit basis. If the accumulator contains 00110101B, then the following operation logical instruction is ANLA hash 01010011B leaves the accumulator holding 00010001B. This instruction is illustrated below. 01010011 immediate data, AND 00110101 original value of A, 00010001 result in A after ANDing operation. Since the addressing modes for the logical instruction are same as that of arithmetic instruction, the AND logical instruction can take several forms. ANLA 55H direct addressing, ANLA @R0 indirect addressing, then comma R6 register addressing, hash 33H immediate addressing. All logical instruction using the accumulator as one of the operands execute in one machine cycle. The other take two machine cycles. Logical operation can perform on any byte in the internal data memory space without going through the accumulator. The XRL direct hash data instruction offers a quick and easy way to invert ports as in XRL P1 hash 0 FFH. This instruction performs a read, modify, write operation. The 8 bits at port 1 are used, then each bit read it exclusive or with the corresponding bit in the immediate data. Since the 8 bits of immediate data are all ones, the effect is to complement each bit by A or 1 is equal to A complement. The result is written back to the port 1. The rotate instruction RLA and RRA shift the accumulator 1 bit to the left or right respectively. For a left rotation, MSB rolls into the LSB position. For a right operation, LSB rolls into the MSB position. The RLCA and RRCA variation are 9-bit rotates using the accumulator and the carry flag in the PSW. If, for example, the carry flag contains 1 and A contains 00H, then the instruction RRCA leaves the carry flag clear and A equals to 80H. The carry flag rotates into the accumulator 7 and accumulator 0 rotates into the carry flag. The swap A instruction exchange the high and low nibbles with the accumulator. This is a useful operation of BCD manipulation. For example, if the accumulator contains a binary number that is known to be less than 100 in decimal system, it is quickly converted BCD as follows. Move B hash 10 div AB swap A add B comma A. Divide the number by 10 in the first two instruction leaves the 10 digit in the lower nibble of the accumulator and the 1 digit in the B register. The swap and add instruction moves the 10 digit to high nibble of the accumulator and the 1 digit to the low nibble. Data transfer instruction. Internal RAM, the instruction that moves the data within the internal memory space, execute it either in 1 or 2 machine cycle. The instruction format is move destination source. Allows data to be transferred between any two internal RAM or set SFT location without going through accumulator. Remember, the upper 128 bytes of data RAM 8032, 8052 are accessed only by indirect addressing, and the SFRs are accessed only by direct addressing. A feature of the MCS51 TM architecture differing from most microprocessors is that the stack resides in one chip RAM and grow upward in memory toward higher memory addresses. The push instruction first increment the stack pointer, then copies the byte into the push or pop. Use direct addressing to identify the byte being saved or restored, but the stack itself is accessed by indirect addressing using stack register. This indirect addressing means the stack can use the upper 120 bytes of internal memory on the 8032 8052. The upper 128 bytes of internal memory are not implemented in 8031 or 51 devices. With these devices, if the SP is advanced above 7FH, corresponding 127, the pushed bytes are lost and the popped bytes are indeterminate. Data transfer instructions include a 16-bit MOV to initialize the data pointer DPTR in program memory or for 16-bit external data memory access. The instruction format XCHA source causes the accumulator and the address bytes to exchange data, and exchange digit instruction of the form XCHDA @RI is similar, but only the lower order label are exchanged. For example, if A contains F3H, R1 contains 40H, and internal RAM address 40H contains 5BH, then the instruction SCHDA @R1 leaves A containing FBH and internal RAM location 40H containing 53H. External RAM. The data transfer instruction that move data between internal and external memory use indirect addressing. The indirect address is specified by a 1 byte address @RI, where RI is either R0 or R1 of the selected register bank, and a 2 byte address @DPTR. The disadvantage in using 16-bit addresses is that all 8-bit of port 2 are used as high byte of the address bus. This precludes the use of port 2 as an I/O port. On the other hand, 8-bit addresses allow access to a few K bytes of RAM without sacrificing all of port 2. All data transfer instructions that operate on external memory execute in 2 machine cycles and use the accumulator as either the source or destination operand. The read and write strobes to external RAM, RD or write, are activated only during the execution of a MOVX instruction. Normally, these signals are inactive, high, and if external data memory is not used, they are available as dedicated I/O lines. Lookup tables. 2 data transfer instructions are available for reading lookup tables in memory space, that is to program memory. Since they access program memory, the lookup tables can only be read, not updated. The mnemonics is move C. Move content. Move C uses either program counter or data pointer as the base register. The instruction is move C A @A plus DPTR. Can accommodate a table of 256 entries numbered from 0 to 255. The number of the desired entry is loaded into the accumulator and the data pointer is initialized to the beginning of the table. The instruction move CA @A plus PC works the same except the program counter is the base address. The table is usually accessed through a subroutine. First, the number of the desired entry is loaded into the accumulator, then the subroutine is called. The setup and call sequence will be move A, enter the number, call lookup, There will be lookup table, then lookup INCA, move C A at a rate A plus PC, return table DB. The table immediately follows the return instruction in the program memory. The INC instruction is needed because the PC points to the RET instruction when MOV C executes. Incrementing the accumulator will effectively bypass the RET instruction when the table lookup takes place. Note, however, that even though we would expect to get a table of 256 entries when using this technique, we only get 255 entries in this case, since we lose one entry due to the effect of the INCA instruction. Consider the entry number of 255 to recycle back to 0. Since the accumulator is 8-bit in size, the next instruction, move CA at a rate A plus PC, would attempt to load the accumulator with the value of RET, which is invalid. Therefore, valid entries are only from 0 to 254. Boolean instruction. The 8051 processor contains a complete Boolean processor for single bit operation. The internal RAM contains 128 addressable bits and the SFR space supports up to 128 other addressable bits. All port lines are bit addressable and each can be treated as a separate single bit port. The instructions that access these bits are not only conditional branches but also a complete repertoire of move, set, clear, complement, or an AND instruction. Such bit operation one of the most powerful feature of 8051 family microcontrollers. This is not easily obtained in other architecture with byte-oriented operations. The available Boolean instructions are shown in the appendix. All bit access use direct addressing with bit address from 00 to 7FH in the lower 128 location. So the example is given below. ACTB P1.7 and turned off by clearing the port bit. CLR P1.7, it is port 1 of 7th bit. The assembler will do the necessary conversion of the symbol P1.7 into the correct bit address as 97H. Note how easily an internal flag can be moved to a port pin. Move C, flag, move P1.0, C. In this example, flag is the name of an addressable bit in the lower 128 location or the SFR space. So, carry bit in the program status word is used to sign bit accumulator of the Boolean processor. The carry bit has also a direct address and this is shown over there, CLRC, CLRCY. CY where defines bit address of 0 to 0D7H. Both have the same effect. However, the former is a 1-byte instruction whereas the latter is a 2-byte instruction. In the latter case, the second byte is direct address to the specified bit with a carry flag. So these are showing over there how the port is activated with the AND gate. So port 1.0 for 1.1 and output is port 1.2. Logical operations such as AND or NAND, NOR for single bit variables. And this is showing over there. Loop move C P1.0 1 cycle, ANLC P1.1 2 cycle, move P1.2 C 2 cycle, SJMP loop 2 cycle. above converts the index for loop. It is shown where CJNE hash 0311 skip, SJMP terminate, then skip. Since a jump occurs only if A is not equal to the control C, a skip is issued to bypass the terminating jump instruction except when the desired code is read. If there is big, if the value is accumulated in greater than equal to 20h, the following instruction could be used. CJNE hash 20h S plus 3. Subroutine and interrupt. There are two variable calls are there, call instruction A call and L call, using absolute and long address respectively. As JMP, the generic call mnemonic may be used while Intel's assembler if the program does not care which way the address is encoded, and it will be shown with a return. Conditional jump. The 8051 offers a variety of conditional jumps with the JNZ instruction that return to the corresponding point. So this is an example. Move loop. Then there may be a lot of steps may be there depending on my requirement, on your requirement of the program. Then R7 hash 10 begin loop. There are a lot of steps. Then end loop. DJNZ R7 to loop. JNZ big. So we are ending the session. These are the references.